Hello everyone, welcome to Inside Science Center. I am Pushkar here and let us study vector algebra part 2. So in our previous part, we had already seen introduction, understanding directions, basic concepts and types of vectors. In this part, we'll study about vector addition, subtraction, sections formula, dot product, cross product, box product and more about tensors. So let us begin with vector addition. So before understanding vector addition, let us understand what position vectors really are. Position vectors are vectors whose initial point is our coordinate reference point. So coordinate reference point is nothing but our origin. So I'll write down position vectors are vectors whose initial point is origin. So in this diagram, it's quite obvious that if origin is here and let this point be A, let this point be B, then OA vector and OB vector are position vectors, and these two position vectors are obviously co-initial vectors because their initial point is the same. So what is the relationship between co-initial position vectors and vector addition, vector subtraction? Well, it is intuitive that if I have to travel from O to B, there are lots and lots of ways, but there is also this one way where O to B vector, like I can travel from O to B by first traveling O to A vector, then from A to B vector. Essentially what I am doing is OB vector is equal to OA vector plus AB vector. Is it clear? If I have to draw it geometrically, I'll draw this AB vector. And you can already see that it's kind of forming a triangle. And this is essentially what we'll see in more details, this triangle law of vector addition. Let's understand addition, subtraction in component form first. So let me have two vectors. Let this be our original point O. Let's say we have a point A over here. Okay, so this is a point A. So this point A, how can I go from O to point A? Well, there are lots and lots of ways, but essentially one way can be I'll go, let's say 1, 2, 3, 4, 5, 6, 7. This is 7 centimeters, let's say. So 7 centimeters, I'm going in I cap direction, and then I'm going in 1, 2, 3, 5, 6, 10. Going 10 in J cap direction, correct? So I can write OA vector to be 7 centimeters I cap plus 10 centimeters J cap, correct? Write down here this 10 centimeters in J cap. What will happen if I draw another vector? Let's say I have another point B over here, let's say. So this will be our OB vector. So can you guess what OB vector can be written in component form? Well, we can write 7, 8, 9, 10, 11, 12, 13. We can write OB vector as 13 centimeters in I cap and 1, 2, 3, 4, 5, 6, 7. Correct? Is it 7? 1, 2, 3, 4, 5, 6. Sorry, 6. 6 centimeters in j cap. So what will this AB vector be? Maybe I'll use another color. Well, this AB vector covers how much distance on the x-axis? It covers 1, 2, 3, 4, and 5, and 6. It covers 6 centimeters on the x-axis, and it's covering 1, 2, 3, 4 centimeters on the y-axis, isn't it? So essentially what I'm doing is, this is 7 centimeters, and this is 13 centimeters. So AB vector has this much distance yet to cover on the x-axis, this blue vector, and this is nothing but how much? This 13 minus 7. So 13 minus 7 gives us 6 centimeters in I cap, correct? And also on the y-axis we have 10 centimeters, correct? 10 centimeters j cap, and then we have 6 centimeters. This is 6 centimeters for B. So how many centimeters did we come down from 10 to 6? We came down by 4, correct? So essentially what we are doing here is OA vector plus AB vector is equal to OB vector. So I can simply solve it for AB vector. AB vector is OB vector minus OA vector, and I'll simply substitute the values here, and I'll get AB vector is equal to, OB vector is 13 centimeter I cap plus 6 centimeter j cap minus OA vector. OA vector is 7 centimeter I cap plus 10 centimeter j cap to get AB vector is equal to 6 centimeter I cap and minus 4 centimeter j cap. So are you understanding what AB vector is? AB vector is not pointing in I cap plus j cap direction. It's not, if you were to understanding it from east west north south directions, if east west north south is more clear to you, if this, let's say this is E cap, and let's say this is N cap, let's say this is north direction, this is east direction, AB vector is not pointing in the northeast direction, it's pointing towards the southeast direction, correct? So that is why I have written here 6 centimeter I cap and 4 centimeter minus j cap. Okay, so this is how you add and subtract in component forms. Basically, you just add I cap with I cap and j cap with j cap. So in a simpler way, I can write it down that if I have a vector A is x1 I cap plus y1 j cap plus z1 k cap, and I have a vector B x2 I cap plus y2 j cap plus z2 k cap, and if I were to add these two vectors, then A vector plus B vector will be simply adding their components together. So x1 plus x2 I cap plus y1 plus y2 j cap and z1 plus z2 k cap. It's quite straightforward, it's quite easy. Similarly, if I do A vector minus B vector, then I get x1 minus x2 I cap plus y1 minus y2 j cap plus 1 k cap. Simply add their components with their components, like I cap with I cap and j cap with j cap, k cap. Okay. So coming to triangle law and polygon law of vector addition subtraction, it is essentially what we had seen right now. This is O, this is A. So OA vector plus, let's say, AB vector, OB vector. Correct? So basically what's happening here is, if I were to add two vectors, I'm placing OA and AB head to tail, and when I'm placing it head to tail, such that tail of AB joins head of OA, then tail of first vector and head of the last vector gives us our resultant vector, which is OB. This is nothing but OA plus. So this is what triangle law of vector addition is. And to generalize it in polygon law of vector addition, what we are going to do here is simply, I'll write down, this is OA vector, this was AB vector, this was OA vector, basically, which is addition of these two vectors. I can simply pick and place this vector. Correct? I'll simply take this vector. I can pick and place them. And it will be here. So this is nothing but our AB vector. We are just picking up that vector and placing it here. And similarly, we are picking and placing this OA vector. So essentially, from a triangle, we can form this polygon, or in another way, if you want to just understand it another way, OA plus AB is also OB, and OC plus CB is also equal to OB vector. But the interesting thing to note here is OA vector is equal to CB vector, and OC vector is equal to AB vector. These two vectors are equal. They are not co-initial, but they are equal. How can we say it's not? How can we say it's equal, since it's, because we can essentially pick and place vectors. See, we are not changing its direction, nor are we changing its length. So nor am I changing its unit. So these two vectors, AB vector and OC vector, are equal vectors, but they are not co-initial vectors. Okay. So this is how I can form a parallelogram from the triangle law of vector addition. This was a triangle law of vector addition. This was a parallelogram of vector addition. And if we look in this picture, if I want to find this AC vector, so how can I travel from A to C? Okay, so let us understand this. Let's say I'm considering this OA vector. So we can also form a triangle which is OAC, and in triangle OAC, I can write OA vector plus AC vector gives me OC vector, correct? Because again, OA vector and AC vector are connected head to tail. The tail of AC vector, which is A, is connected to the head of OA vector. So I can write OA vector plus AC vector gives OC vector. So if I want to find what AC vector is, AC vector can be written as OC vector minus OA vector. So let's understand what is happening over here. This first diagonal OB of this parallelogram, this OB, is the sum of OC and CB vector, OC vector and CB vector. Whereas the second diagonal AC is the difference of OC vector and OA vector, OC vector and OA vector. So what parallelogram law of vector addition says is that if I have a parallelogram whose base vector is, let's say, A vector, let's say this vector is B vector, so it naturally means if this vector is B vector, then this vector is also B vector. I'm just picking and placing it. And similarly, if I am picking and placing this A vector can be picked and placed here. Correct? So this first diagonal represents, what does it represent? Well, it represents A plus B vector, correct? Since OC vector was our A vector, CB vector was our B vector, then OB vector was nothing but A vector plus B vector. And similarly, this second diagonal is nothing but our AC vector. AC vector is nothing but OC vector minus OA vector, and OA vector was nothing but my B vector, correct? So OC vector, which is our A vector, I'm subtracting it with B vector to get AC vector, so I can write the second diagonal is A vector minus B vector. So parallelogram law of vector addition says that this diagonal is the addition of two vectors, whereas that other diagonal is the subtraction of two vectors. Okay? If we extrapolate this idea, we can understand what polygon law of vector addition or subtraction says. And what polygon law of vector addition subtraction says is, if I join lots and lots of vectors in this manner such that the final point of first vector becomes the initial point of the second vector. Let's say I have a few vectors. Let's say this is A vector, this is B vector, this is C vector, this is D vector, this is E vector. So in this diagram, all these vectors are connected such that the tail of the next vector is joined to the head of the first vector. And what will be the addition of all these vectors? Well, it will be basically the initial point of the first vector joined to the final point of the last vector. So in short, we have covered this displacement. This is the resultant of all these vectors. This vector is nothing but A vector plus B vector plus C vector plus D vector plus E vector. So this is what is the polygon law of vector addition. And there are lots and lots of questions based upon this polygon law of vector addition, such as, let's say if we have a regular hexagon, the property of a regular hexagon is that magnitude of all these vectors are the same. And also the angle between them is also the same. If I have a regular hexagon like this, let's say I have this A vector, B vector, C vector, D vector, E vector, and F vector. So there are questions like, what is the addition of all these vectors? What is A vector plus B vector plus C vector plus D vector plus E vector plus F vector? What do you think it is? Well, it is 0 because the final point of F is the initial point of A. So in short, we have gone nowhere. We came back to the original place from where we started. So addition of all these vectors is 0. So this is what the polygon law of vector addition is. So I think it's all becoming clear now what parallelogram law of vector addition says. The first diagonal is the addition of two vectors. The second diagonal is the subtraction of two vectors. What triangle law of addition subtraction says? Triangle law says that, yeah, it's basically the polygon law. Just join the heads and tails, the initial points accordingly, and then you will get the resultant vector. Let's move on to addition and subtraction of vectors in magnitude form. So if I have this diagram from earlier, this parallelogram, and I want to find what is this A vector plus B vector. This is our A vector plus B vector. How do I find it? Well, to find this vector, let us first consider some our basis directions, and my basis is nothing but I'll consider this to be my first basis vector. Let's say this is I cap, and then perpendicular to I cap, let's say this direction. Let me represent it by, okay. So in this diagram, if this angle is theta, then this angle also has to be theta. And let's say if magnitude of A is A and magnitude of B is B, then I can simply split B into two components as we had seen in the previous class. So we had seen in the previous class that in 2D vectors, correct, I can split it into components. Like we had split it here, y was r sin theta, x was r cos theta. I'll do the same thing here. I can write A vector as simply as A I cap, but for B vector I can split it into two components. I can write B cos theta I cap plus B sin theta j cap, correct? You can split it into two components. And since I wanted to add these two vectors, I'll simply add them. How will I add them? I'll add it in the component forms. A vector plus B vector can be written as A I cap plus B cos theta I cap plus B sin theta j cap. And well, we had studied that we can only add the similar components. So I can add I cap with I cap and j cap with j cap, but I don't have any other j cap other than B sin theta. So A vector plus B vector can be written as A plus B cos theta I cap plus B sin theta j cap. So this is how I can write it. And this is A vector plus B vector. But now I want to find out its component, its magnitude. So how do I find out its magnitude? Well, we can use Pythagoras theorem. So I can write magnitude of A vector plus B vector to be the root of squared of the first component, which was the first component, A plus B cos theta. A plus B cos theta whole squared plus the second component was B sin theta. So B sin theta's whole square. Correct? We had seen how to interchange between magnitude form and component form. Correct? This is how this was for 3D. For 2D, it was, we can simply write x squared plus y squared. But in this case, our x is what? What is our x? This is A plus B cos theta's whole square and B sin theta whole square. Let me simplify it. I can use the whole squared formula. So I can simplify it to modulus of A plus B written as under root of A square plus B square cos square theta plus 2ab cos theta. Simply I am writing down the whole squared formula, a squared plus b squared plus 2ab. But then b is nothing but b cos theta. And similarly I can write for b squared sin squared theta. And if we look at these two terms, this is my first term and this is my second term. Well, I can take b squared common. After taking b squared common, what I get is magnitude of a plus b vector can be written as under root of a squared plus b squared common, so cos squared theta plus sin squared theta, and the 2ab cos theta remains as it is, 2ab cos theta as it is. And what is cos squared theta plus sin squared theta? Well, from basic trigonometry, we know that it is 1. So magnitude of a plus b gives me this beautiful formula called as a square plus b square plus 2ab cos theta. And if I want to draw this, how can I draw this? Well, instead of drawing b in the magnitude form, let me just write down the components of b. So this is a vector. I am writing down this is b cos theta I cap vector. And then I am writing b sin theta j cap vector. So this was my b vector, that this dotted line is my b vector. But then resultant vector of a and b is nothing but this is my b vector, but then resultant of these two vectors is the initial point of a and the final point of b. This is a plus b. And from this diagram, if we also want to find out what is this angle between a and a plus b, the angle between a and a plus b can be found out easily. How? Well, angle between a and b can be written, I can write the tan phi is nothing but the perpendicular upon base. So in this right angle triangle, what is the perpendicular? Perpendicular is nothing but b sin theta. And what is base? Base is a plus b cos theta. Right? And phi is equal to perpendicular is b sin theta upon a plus b cos theta. Note that phi is the angle between a plus b and a, and what is theta? Theta is the angle between a and b. Don't get confused with this theta and this phi. So this is how we can find out the addition and subtraction in magnitude form. I'll give you a homework, and homework is simply you have to find out what is a vector minus b vector. You can use all these steps that I have used, but instead of doing plus here, you just have to do minus, you just have to subtract and then find its magnitude and find the angle phi. It's easy, just try it out. You'll get a similar formula and you'll get magnitude of a plus b is the root of a squared plus b squared. Instead of getting plus 2ab here, you'll just get minus 2ab. Yeah. And similarly, just try to find out what angle it is. Okay. So I guess we'll stop our today's lecture here, and in the next lecture we'll study in details more about sections form. So in this lecture we have covered addition and subtraction of vectors. I know we have only covered one topic, but since we have covered it in details, I hope you don't have to face any problems further. The next lecture will try to cover all these remaining topics.